So in last video, I was talking about reflection in a plane surface or a smooth surface. There's another type of reflection, and this type of reflection is much more common for us to see. We just don't pay attention to it. So most objects are actually visible due to a property of light called diffuse reflection. So this is the other type of reflection. So if you take a look at the picture here of the tree, when you get sunlight hitting the tree, each point of that tree is going to reflect light in many different directions, right? So if the light hits here on the tree, it's not just going to bounce back straight or in one single direction. That light is going to bounce in lots and lots of different directions. And this is happening on the entire tree, right? Versus just the one point, like what we saw with the plane mirror, where the light comes in, it hits, and it bounces out in a single direction. You can see the same sort of thing happening down here, where instead of a nice smooth surface, we have a rough surface. So think about like gravel or grass, something like that. The light comes in at that angle, but none of it really goes back out at the exact angle in the other direction. It bounces in all different directions. And so this is diffuse reflection. So you can see the tree from many angles. You can see the gravel from many angles because of this diffuse reflection. It spreads that light across a big area. This is also why when you walk like in the forest, it's not completely dark under the tree, under the forest area, because some of that light, as you can see here, gets bounced down. And so this lights the under part of trees. Diffuse reflection can happen in the same places that we can get what they call specular reflection or that mirror reflection. So you can see this is the same building. Here is when the water surface was incredibly smooth, so we got the mirror-like reflection. On a different day, though, you get diffuse reflection because the water surface isn't smooth, it's bumpy. And that makes the image blurred. And so this is a property that is incredibly important to our everyday lives since we use this to see. For example, the room that I'm in, the room that you can see behind me, is actually being lit right now by the diffuse reflection of the small amount of sunlight that comes in through the window. My blinds are actually closed behind me here. There, behind me there. But there's still enough light coming in and bouncing around in the room to light up the things that are behind me. So diffuse reflection in action, this is something that some of you may have experienced, whether it's when you've been driving or when you're trying to take, photo shoots or something like that. Because, for example, road surfaces are going to determine the amount of diffuse reflection. So think about if you're driving at night and you are driving on a regular road and it's dry. The road surface is going to be rough. So you're going to get diffuse reflection. Your headlights are going to hit the road in front of you, and it's going to hit the road, and just like we saw in that previous picture, the light rays are going to bounce in all different directions. Right? And so they're going to light up not just the road in front of you, but they're going to light up the trees around you. They're going to light up the road farther down so that you can see a wide area and an area pretty far in front of you. So it lets you see the road ahead and the road to either side at night pretty well. This is very different when it's raining. When the road is wet, you get what you see down here. The wet road surface gets filled in. So there's not a rough road anymore. It acts more like one of those plane mirrors. It acts like a flat, shiny surface. And so it's not going to act as much as diffuse. And so seeing the road is going to be a lot more difficult. So if, again, you've been driving down the road after it's rained, think about it, your headlights don't work as well. And this is because your headlights go out, they hit the road, and they're actually going to mainly bounce up and away into the sky. Not very helpful. So they don't spread the light around out to your sides and out in front of you so you can see. So it reduces the amount of light you can see. And if you're doing some sort of shoot, for photos and so forth, this can be something maybe you're looking for, or it can actually cause problems because it's going to cause a lot more reflections in what you're working on. All right, so as I mentioned, when light interacts with materials, there are different options. So one is reflection, like I've been talking about. So the light can bounce off of the object. Other options, it can be absorbed. And so materials that are what we call opaque are materials that are going to absorb light without re-emitting it. So we'll see there are other options, which is that they can absorb them but then let the light back out. But opaque materials absorb the light without re-emitting it. So they're going to keep the energy from those light waves. So what are some examples of opaque materials? So think about what are things that are opaque. These are items that you can't see through. So most of the materials that we see every day are considered opaque materials, meaning that they absorb some of the light without re-emitting it. So what does this do to their thermal energy, to their heat? Well, for most of the objects, it increases it. Think about if you have a dark colored shirt on in the middle of summer, you're going to get hotter. And that's because that dark colored shirt is going to absorb the heat, or absorb the light, and convert it into heat. So that's what's going to happen to these objects that are opaque, because they're absorbing the light, not reflecting it or transmitting it or refracting it, the other options we've got. Now, some light is often reflected from these opaque objects, and that's what creates color. And so we'll talk about that in a little while. It's called selective reflection. So, the only objects that actually absorb all of the spectrum are those that appear black, because they're absorbing everything and reflecting nothing back to us. Metals are opaque to light, but they don't absorb much of that light. Instead, they reflect it, which is why they appear shiny. So they are considered opaque, which is why we can't see through them, but their property means that they are going to reflect a majority of that light instead of absorb it. They will absorb some of it, which is why they become hot, but a majority of it is going to be reflected on metals. All right, if you are not an opaque material, you're going to be a transparent material. And that means that you're going to allow light to do something different. These are materials that allow some or all of the frequencies of visible light to go through. So we'll see there is, just like there's selective reflection, there is selective transmission, or transparent materials that allow only some light to come through, and we'll talk about how that works. So what are some transparent materials that you can think of? So these are materials you can see through. Most commonly, we think of the one that's down here in the example, glass. But other common materials that are transparent, things like plastics are commonly made to be transparent. Also, water is a transparent material. So these are materials that are going to allow some or all of those visible frequencies to come through. Now, what's interesting about transparent materials is while they will let some or all of the frequencies of visible light through, as you can see here, glass is going to allow the visible light to come through, but it doesn't allow the other two sides of the electromagnetic spectrum close to visible light to come through. So the glass is going to block ultraviolet light and infrared light from coming through. And that's part of why glass starts to feel warm, for example, when sunlight shines on it, because it's blocking and absorbing those frequencies instead of allowing them to come through. So there we go. So the low and high frequency waves can't pass through. Instead, they get absorbed and generate heat. So this is why glass gets warm to hot, depending on what is going on in the sunlight, when those materials get exposed to sunlight, because they will not allow that ultraviolet or infrared energy to pass through. So let's take a look at the speed of light in transparent materials, because we can't talk about it in opaque materials since it can't travel through. So a little bit different than when we looked at sound. So sound, we were fastest in solids. Let's look at the speed of light, the speed of light. So the speed of light is going to be fastest in a vacuum. So where there's no materials to slow it down, it's going to go fastest. So the speed of sound, remember, was about 320 to 330, 340, depending on the temperature, meters per second. I told you that light is a lot faster. Well, here we go, 300 million meters per second. So a lot faster. And that's in a vacuum. Here in our atmosphere, it's going to travel a little slower than that. So in a vacuum, we call it C. In the atmosphere, it's slightly less than C, but we go ahead and round it off because it's pretty close. So we basically use the same value for both the vacuum and the atmosphere. So when we move into a liquid like water, because it's transparent, the speed of light goes down. So it's only 3/4 of the value of C. So it's only 3/4 of this value. When we move into glass, depending on the type of glass that it is, it's going to be 2/3 the value of the speed of sound in a vacuum. And then diamond, it's going to slow down even more. We're going to go down to 0.14, so less than half the speed of light in a vacuum. So what's the difference? It's actually because of the same reason why the speed of sound increased as we went from gas to solid. But let's take a look at what happens when light travels through a material like glass. So here is a pane of glass. Here's our incoming light ray. It's energy. It's going to hit an atom. So the atom eats it. I love this little diagram. And then it's going to spit it out and get eaten by the next atom, and repeat until you get to the other side, and then it's going to get ejected out. The thing is that when this happens, it slows down the light because it has to travel from atom to atom to atom. And the denser the solid, so between glass and diamonds are much denser, the atoms are much closer together, the light energy has to be passed from one atom to the next, and in diamonds there are more atoms that it has to be passed to. So give you an idea. So, this is glass. So diamonds instead would be like this. These would be each of the atoms in the same pane. So if this was a diamond glass pane or a diamond pane, then these all would have to have the energy passed through them before it got to the other side. So that energy from the photon, the light wave, is going to transfer. And every time the energy gets transferred, some of it's going to get lost. So not only does the speed slow down, but some of that energy is going to get absorbed by those atoms as it travels. All right, Our next video is going to pick up with color.